Hi everyone. I'm very happy to have you join our seminar today. Professor Rebekka Burkholz is currently a tenure track faculty position at the CISPA. And the main goal of her research is to gain a theoretical understanding of deep learning from a complex network perspective and to improve contemporary machine learning algorithms. And previously, she was a postdoc at Biostatistics Department at Harvard Chan School of Public Health. And before that, he also hold a postdoc researcher at ETH Zurich at the Institute of Machine Learning. And she obtained her PhD from Frank Schwarzer as the chair of system design. And without any further verbals, please enjoy her talk today. Thank you very much.
Thank you very much for the kind introduction and also, the invitation. It's a big pleasure to be here and to share with you some of our results on pruning deep neural networks for lottery tickets. So thank you for so much for being here. Of course, the first question that might come to your mind would be, why do we want to prune neural networks? And one of the big challenges that neural networks become larger and larger, and they become overparameterized. So this seems to be essential to achieve a high accuracy of these deep neural networks. However, this also comes with certain costs. So larger overparameterized neural networks achieve a higher accuracy, but it also means that often contributions are limited to large labs that can afford the computational power that is required to train these networks and all the whole infrastructure and fulfill all the memory requirements that are actually quite heavy. Or they can also afford to train on large scale data and even get access to this large scale data. So we have the problem that, if we want to democratize deep learning, we need to find ways to train smaller scale models that actually perform well in practice and achieve a similar performance as these large scale models that we are currently training. So, of course, this then begs the question, do we really need these large models? And we need to solve two challenges if we want to train smaller scale models. One would be the structure learning. So let's assume we really want to train smaller scale models. And the question is, how should these look like? So, and there are different approaches on how to do that. For instance, Wu Yang has also contributed, great papers in this area. So, for instance, to the neural architecture search, but we might also want, we could also augment neural networks. So start very small and then try to make them bigger. But how pruning is usually a more, let's say, a successful strategy because we can still leverage this overparameterization to solve a second problem and challenge that we face. And this is the optimization of these neural networks. So for these, it's super critical to initialize them right, to regularize them, define all these different learning schedules that we potentially need to adapt if we want to actually find ways to optimize small scale problems. Because the big challenge right now is that the standard algorithms that we use to train neural networks is stochastic gradient descent. And this is a local optimization algorithm, which means we actually need to start close to a solution already that to allow a successful or to enable a successful optimization. And overparameterized neural networks have different properties that seem to aid us in this optimization so that it's not that difficult to initialize them and to optimize them. But the sparse lottery ticket hypothesis by Franklin and Garbin has given us hope that it's actually still possible to find initialization schemes of sparse architectures and that these sparse architectures exist to solve problems. So the recent lottery ticket hypothesis states that there exists a small, well-trainable subnetwork of a large randomly initialized source neural network. So this means there actually exists a subnetwork that can be trained in isolation and can achieve at least the same performance as that we would achieve if we would train the dense neural network, so the original network. So it solves our problem. However, this is not everything. There were even Ramanujan and collaborators went even further and stated the strong lottery ticket hypothesis that says that there exist small well-trainable subnetworks of random dense networks that perform already valid initialization. So they don't require any further training except from the pruning. And this is actually a statement that we can prove. So that we can also, we can understand theoretically why that is possible or how this could be possible. And this is so interesting because it also gives us another way, or it shows cases as it shows a path that we could maybe even get rid of this general optimization algorithm SGD that we use to train really large overparameterized neural networks, because we could actually also prune larger source networks, but random source networks instead. So, but why could we need a theoretical contribution in this area? Why do we want theory? And the reason is that there is that a specific problem has been observed, also by Franklin and collaborators. They found that contemporary pruning algorithms cannot find lottery tickets in large, really complex neural network structures, unless they resort to rewinding or fine-tuning. So there are some techniques, however, they give up on the lottery ticket hypothesis. And currently, we need to use expensive pruning training iterations to identify those tickets. So we are not there yet that we can identify and train a small-scale neural network structure from scratch. But should this be feasible? Our theory states now conditions when the pruning algorithms have a chance to succeed. So when there exist actually solutions that we were looking for. And by the way, it's important remark, please always interrupt me if you have questions, so that we can totally adapt the speed of how fast we go through that. And I'm happy to take questions also during the talk, because I think it's much nicer when it's interactive. So feel free to ask whenever something comes up. So now that we are at this point, that we want to establish a theory for the existence of lottery tickets, we should also mention that there has been done great work in this area already. So Malach and collaborators, for instance, presented a construction of lottery tickets that needed the source network to be 2 times as deep as a potential target network. We'll see in a moment what I mean with that. The only problem is that the width requirement was polynomial in the error that we can make, which is a really bad in terms of it's a really tough requirement. So this would mean that we would need really large networks in order to succeed. Pensia and collaborators have then shown that this is not necessary. We only need a logarithmic overparameterization in comparison to a target network. And they leveraged subset sum approximation results for that. And then Dacuna and collaborators have also shown existence result not only for fully connected networks, but also more realistic or often used architectures like convolutional networks, but they required positive inputs. And here, what I'm going to share with you today are some results that improve the construction that we know by leveraging the available depths of the source network in a better way. So we only need, so essentially our lottery ticket and our will have almost the same depths as the source network that we are pruning. And it will apply to general activation functions and not only ReLUs as previous work. And we can cover, general architectures, the contemporary often used architectures like CNNs and ResNets. And if you're interested in more details, then please feel free to check out these recent papers. But also feel free to, of course, to ask for more details right now during this talk. I'm happy to provide those. So what is this general existence setup, the proof setup? So to go also a little bit into the math of these problems today. So we assume that usually we have a target network, and this target network solves the problem of interest. So this is, of course, a strong assumption, right? So we assume that our task right now is solvable with this target network. And now we also assume what is given to us. So the target network, we don't know this in practice, right? We just assume right now for theoretical purposes that it exists. But in general, we would like to find that. What we have actually is a source network. This is randomly initialized, and it's potentially larger and also dense. And what we want to find is a subnetwork, the lottery ticket, that approximates this target network. So we get this by pruning the source network. And it approximates, so it represents a similar function as the original target network, and this way solves our problem. And we can now, derive different existence results that are of the following form. So we have, so the main theorem says that, given this target network, we know, given that this target network has a certain width, this is this NT, and also a potential depth, this is this L. We can have now requirements on the source networks that will guarantee us that there exists a lottery ticket, so a subnetwork that approximates the target network with a certain probability, with probability 1 minus delta. And if this delta is small, then we have a very high probability that we actually successful and we can find these tickets. But what's very interesting about this theorem is now that in comparison, here on the left side, you see now the widths that we need in every, or let's say the maximum width of a layer that we need in the source network that we prune, that this needs to be larger than the one of the target network, but only by a factor that is logarithmic in the error that we're allowed to make. This is the epsilon, and also logarithmic in our failure probability delta. And this is now a really strong result because it means that this is actually realistically, this could be feasible. So how do we get there? I would also like to discuss only the main proof ideas today with you. So what we're essentially going to do is, you don't need to understand exactly what's going on yet. I will explain that, but we essentially will discuss 3 ideas. And one is that we will use the activation functions that we have to approximate the identity function, because this will allow us to construct multiple copies of neurons in an intermediary layer. And this will allow us then we will leverage these kind of subset sum approximation results that I have mentioned already, that will allow us to get this logarithmic overparameterization and not something that is proportional, for instance, to 1 over epsilon or something like this. So what are we going to do?
Oh, hi, Rebekka.
Yeah,
May I just quickly one short question. So in the previous several slides, you are still assuming that the small approximation error is measured as the initialization of this lottery ticket, right?
Yeah, so the approximation error will be the final one. So once we have the lottery ticket and we make an epsilon error in comparison to the target network in the function that we represent, and this is usually with respect to a suitable norm. So this can be, for instance, the supremum's norm, or can also be the L2 norm or something like this of the output, but of the final output of the network.
I see. And or to say that you will not train this F epsilon, right?
Oh, sorry, could you repeat that question?
You will not do any training for this F epsilon, right? The lottery ticket.
Exactly. Yes, we only prune the source network. Exactly. We don't do any training.
I see. Right. Thank you very much.
You're welcome.
Yeah.
But I could comment on that a bit, because of course, so this is kind of nice that we don't need to train anymore. And of course, that also kind of proves the existence of, I would call it weak lottery ticket. Of course, it's a powerful concept, right? But I call it weak in comparison to a strong ticket, where we need to do additional training. So the strong ticket is also a weak ticket in some sense, because, we could just train it, but it wouldn't change during training, potentially, just because we have arrived already at a good solution. However, we can still expect that we wouldn't need this width requirement that we have here. Oh, you cannot see my, not sure if you can see my
I can
mouse.
See you. Yeah.
Good. So we probably would need less, a less wide source network if we allow essentially to have a higher training, to have a higher epsilon error, if we allow for, if we allow that we can also train the network after we have pruned, because then we can compensate for, more errors that we potentially make during the pruning.
Yeah. I can agree with that. Yeah, thanks.
Yeah, thank you. Thanks a lot for the question. This was very important. Nice. But now that we are here, let's start now with explaining the main idea. So what we are going to do right now is we will explicitly construct now the lottery ticket based on the source network. And we know, of course, we know a target network. So let's assume right now we just have a single layer, because that makes the argument right now a bit easier. So here on the left, you see basically one layer of our target network. It has 2 inputs and 3 outputs. And on the right side, you will see now a lottery ticket. So based on our construction, as you can see, we represent this now with 2 layers instead of 1. in the lottery ticket. And the reason for that is that we create now multiple copies of the input neurons, as you can see here, that help us now to do the approximation. So you can think of that in the following. So the reason why we need that is, I mean, we have a random network, right? And we prune this. So if we search now for something that we could use in this random network, we potentially need to throw away a lot of things that don't match our target or that what we are looking for, right? So because of that, you can assume that we need something wider and we need more choices because you know, we have basically random offers to us that we could choose to keep and not prune away. And since they are random, we need more of them to choose a good one. And this is what is going to happen here with the intermediary layer. So what happens here is that we prune in the first layer, we prune the neurons towards univariate neurons. So we only keep one connection here to get a multiple, essentially, of the input neuron there. And then we can choose among those that we have, we can choose the right ones that we need, for instance, to approximate a specific rate in the target network, for instance, to approximate a connection that we see here. So this is the first thing. And you can think of this right now here in the intermediary layer. Usually you could think of this as the identity, because that would be ideal, right? If we had the identity here, because then we just multiply here the input neuron with something and we can create easily multiple copies of that. However, usually we don't have the identity function there, but we have in the in the original proofs, we would have a ReLU activation function, which is of course very common. And what is special about this ReLU is that we can construct the identity now really easily. So we need only 2 neurons instead of 1. If we have ReLUs now, and we can still do follow the same argument that I just explained. And this is, you can see here also why it's very easy to just create the identity function with this. It's just the sum over a ReLU minus the negative input of the ReLU. But the question is, of course, what do we do now if we don't have a ReLU activation function, but if we have other activation functions? And the main idea there is to approximate this locally only with, for instance, a shifted leaky ReLU, because that allows us to approximate the identity now. We don't get it exactly as a ReLU would allow us to construct it, but we actually approximate it. And as you can see here in the visualization, then the identity construction is very similar to the one of a ReLU. And it's also, in the end, it's also a similar sum or a similar let's say, construction as we had for the ReLU activation function. We just need to essentially divide it by a factor that depends on the properties of the actual activation function. And the additional challenge that we have then in this setting is to take care of the approximation. So to make sure that we only use values that are locally in a region around the origin where our approximation is good. And now we can use these activation functions also here in the middle, and this explains right now, for instance, why we would have here now, for instance, a positive version of an input neuron and a negative version, because we need both, to get the identity in the end. And now let's return to our existence proof setup then. Now we know how to construct a single layer. But as you can see here, for instance, the first layer here, we would need now 2 layers in the lottery ticket and in the source network to construct the first layer, because we need somehow to create multiple versions of the input neurons. However, once we have done that, what is now special is about our construction that we create already multiple copies of the target neurons in the next layer, which means that we don't need 2 layers for the next layers to approximate the next layers, but 1 layer is already sufficient. So all layers except the first layers can be approximated with a single layer in the lottery ticket. And this is important because this allows us now to find relatively sparse representation of the target network. Because what is usually, so how in practice this works is, right, we have the source network and this has a fixed depth. And ideally we would like to leverage the full depth of the source network to get a really sparse representation of the function that we're interested in. So this means that our target network itself can get sparser, and then in consequence, also the lottery ticket can get sparser in this setting. So, but the question is, of course, how much overparameterization do we actually need? So how many versions or how many multiple copies do we need of these input neurons in this context? And ideally, And as you might remember, in our theorem, we had a logarithmic factor. And the question is, where does this logarithm come from? And this is now the subset sum approximation result that we use. This is actually an old result by Lücke in 1998. And Penzier and collaborators in 2020, applied this result to lottery tickets and found and made the connection that this is actually useful and can explain that we only need this logarithmic overparameterization. And the general result goes like the following. So assume we have a target parameter that we want to approximate. This is, for instance, a target weight, or can also be a target bias. We assume now that we have to approximate this, we have random variables available to us that are usually IID, so they're independent, and they are, for instance, distributed as uniform random variables here between -1 and 1. To get this, we can also make this, we can use exactly the setting that we usually have in standard neural network initialization schemes. It's not a big difference in comparison to what I showed you here. This is just easier to present right now. So we assume that now we have m random variables given to us. And we also assume that we set now this epsilon. You can imagine already this error, that we can make a certain error, and we have a certain probability to fail with the construction. This is the delta. These are given to us. And then if we choose now the number of random variables bigger than already something that we, that came up in our theorem already in the statement, if this is now larger than something logarithmic in our failure probability delta and logarithmic in the epsilon error that we are allowed to make, then we can actually we can use a subset of all of these random variables that are available to us, sum them up, and this is then a really good proxy for our target parameter. And essentially what we do is we use now this result for every single target parameter in our network in the lottery ticket construction. And then of course we need to make sure that we don't make too many errors, because these errors add up and propagate through the neural network. And we need to make sure that this, of course, is bounded. But is that actually useful? Because what you can see here right now is we have a constant in here. And this constant is fine from a theoretical point of view, but it could be really large and then make this result completely impractical. So what does this actually mean? And to investigate that, we have done essentially simulations. So we have created, we look at normally at uniformly distributed target parameters, and try to solve many subset sum approximation problems. And it turns out that this constant that we have there in the front is roughly something like 3, which is really relatively small. And this means that subset sizes of something like 10 to 15 random variables are completely sufficient to obtain to obtain good approximation results. And on average, we only need subsets of size 2 to 3 in this context for a reasonable choice of epsilon, of the error that we make, that is sufficient in our neural network context. So this means we only need something like 2 to 3 more parameters for each target parameter in the lottery ticket. So this is essentially the overparameterization. This is what we pay by pruning instead of training. That we have 2 or 3 times more parameters in the end in our construction than we could have if we would, find the target network, which is of course very hard. If we could do that, then this would be amazing. So and this explains now the logarithmic factor here that we talked about, so this overparameterization factor, which is logarithmic now in the epsilon and delta. And then, of course, we also need to take care of that. We need to solve now multiple subset sum approximation problems. So because of that, this logarithm also depends on the number of target parameters that we need to construct, and also the number of parameters in the network. But in practice, this factor is roughly something like 10. So we need, and this is now really feasible. Now we get into a feasible regime. So we need roughly, if we do pruning, and this has also been shown experimentally, of course, that this is feasible. This is how they created the lottery ticket hypothesis and also the strong lottery ticket hypothesis. They showed that pruning random source networks is feasible and achieves remarkable results. And as it turns out, this means like, if this target network, if the source network is wider by a factor 10, then we should be fine. So lottery tickets exist. So coming back to the original question that we had, or the problem that contemporary pruning algorithms somehow have problems finding lottery tickets in large, really complex neural network structures. has some kind of answers. So we can say, well, if the source network is wider than by a factor of approximately 10, then these lottery tickets should really exist with high probability. So what's the issue now? What's the real problem is? So we have two possible explanations, at least. One is there exists simply no sparse target network. So, all our theory kind of, doesn't help us really a lot because, this target simply doesn't exist. So the problem is not solvable. That's one option. The other one is that our pruning algorithms are not good enough yet. But this would give us hope that, if you develop better pruning algorithms, we might have a chance to succeed on the long run. That said, I should mention that this pruning in general is an NP-hard problem. So we cannot expect to always succeed necessarily with that. There will be hard problem instances. However, we can still have usually, this is not a big constraint because we could still have, easy, usually in practice, have simple problems to solve with the right algorithms. So this is not necessarily a limitation for us. So we can ask the question, is there potential to develop better pruning algorithms and solve that issue? Let's investigate that. So let's first start with the first hypothesis. There exists no sparse target. And so the question is, what tasks can we solve with these sparse neural network representations? So, can we come up with problems where we could actually find sparse representations? Because, maybe this would answer our question, at least there should exist some sparse targets. And this is now work with great collaborators, from Harvard and MIT. We investigated this question in a more broader context. So we proved the existence of universal lottery tickets. What do I mean with that? So this is an even stronger concept. So as I mentioned, these pruning algorithms that we currently have and that are relatively successful, they are also computationally quite expensive. I mean, they have become better and they are not as expensive now as training the regional dense network often, but they're still very expensive. So they don't help us a lot in this respect. And for training, for saving for computational costs, they are of course great for improving our inference tasks computationally. But this is in general highly problematic. However, Burkholz and collaborators and also Chen and collaborators figured that these lottery tickets, some are actually transferable. So they have a kind of universality property, which means that we only need to invest the computational resources once or a few times on large-scale problems potentially, but then we can reuse the identified lottery tickets and only train those from scratch on a new data set. So this is exactly what happens. So let's assume you train now, you identify a lottery ticket based, on this example, you want to distinguish different cats. You can still then reuse this lottery ticket and train it from scratch on a similar data set. And of course, as in normal transfer learning, these universal lottery tickets have the tendency to be better transferable if they are trained on more complex data. Then they should transfer to less complex data. And we can explain that phenomenon also with our theory. But let's first, to really understand that, let's formalize this concept of universality. What does that mean? So how would it really help us with our learning problem or simplify the learning task? So for instance, we could say, well, maybe we should only train the last layer. But a one hidden layer neural network has a universal function approximation property. So training already only the last layer is theoretically a really strong concept. But we might need, a lot of features in order to do so. But this is kind of, this is not theoretically, that doesn't necessarily really simplify the learning problem. Another option could be Kolmogorov-Arnold representations. And I will explain you in a moment what that actually is. But this would now allow us to basically reduce the problem to learning only univariate functions instead of multivariate functions. However, these functions are quite irregular, so often in practice this actually does not work. We have tried that. So what else could we do? And the answer we came up with was to learn only a linear function to adapt the ticket. So really only the last layer, the linear part of the last layer. And with lottery tickets, when we have them, no additional pruning is required. So once we have identified universal lottery tickets, they will give us the features that are universally usable and be transferable to a different data set and task. But yes, but we don't need to train that part anymore. To transfer the ticket, we only need to train, the last linear layer. So conceptually, this means we assume now that this last linear layer is trainable, and essentially all the other, the rest of the neural network or of the lottery ticket, the universal lottery ticket, defines a dictionary. So you could also think of it as basis functions. And this defines now our, this is a formal definition of the concept of universality. So we assume right now also that, of course, this only works with respect to a certain function class that is defined on the data. So, and this also explains this observation that Marcos and collaborators had. So, for instance, if you have now trained this dictionary, you identify the lottery ticket on more complex data. This means that your dictionary becomes probably richer. So it's higher dimensional. You have more features, more elements in this dictionary. And we can obtain then, and if this function class is more complex and richer, then of course we can also obtain a higher degree of universality, because if we transfer to a new task, we can, the probability is higher that we can actually make use of these features. But does this dictionary have a sparse neural network representation? Because that was actually our original question, right? Do we have problems that can be solved with really sparse representations? And for this, we looked into specific classes of basis functions, because, a dictionary is fine, but if we want to get really sparse and don't use a lot of parameters, we better stick to basis functions, because we don't want to have more features in our dictionary than we actually need. And the Kolmogorov-Arnold representation that I've mentioned already is actually quite suitable in this context. So the Kolmogorov-Arnold representation, so the basic statement is that we can represent any continuous function in the following form, namely as a composition of an univariate function g here, and a weighted sum over, again, a univariate function that is now evaluated in each input component. And what is special about that is that, according to Schmidt-Heber, the only part that would be now task-specific, potentially, would depend on this, for instance, the basis function or the function that we want to represent, is the w's. So are these weights. The g and the phi would even be given to us. We would know them in the construction of Schmidt-Heber. However, these functions are very irregular and not very useful and not easy to represent sparsely with a neural network, even though they're univariate. However, polynomials have a very nice and amenable Kolmogorov-Arnold representation, where these functions g and phi now depend, for instance, on the polynomial, on itself, or on the structure, but the actual univariate functions are smooth. So they essentially consist of a composition of an exponential function, and otherwise we need a logarithm. That's all. We need to represent an exponential function, a logarithm, and otherwise need to be able to, do compute weighted sums, so a linear function in them. So this is a very simple representation with which we can represent any polynomials. Fourier-Bois's function also have a very simple structure, a Kolmogorov-Arnold structure. So the inner univariate function is even the identity, and the outer part would then be, for instance, a sine or a cosine or something similar. Or we could also represent wavelets that way, but let's for now stick to the polynomials to just exemplify the concept, because what is now a contribution of us is to find a really sparse neural network representation that also makes use of convolutional structures. So as we had this before, the upper layer, right, is task specific. So this we can learn and adapt to any new task. But what we want now to do is to prove the existence of universal lottery tickets, for instance, of polynomials. We want to show now that we can construct these basis functions really sparsely. And if they have this Kolmogorov-Arnold structure, then we can do that with the following form, with a universal lottery ticket. So essentially, we only need to represent the inner univariate function, for instance, the h here. Then a linear layer. This is essentially we learn the weights now of the specific polynomial. So this is polynomial specific now. This would correspond to the exponents of the polynomial, for instance. And then in the next layer, we only need to represent one univariate function. Again, for instance, the exponent or something like this. to represent a basis function. And what is special about now is that the G and the H, these univariate functions, are shared. So we can make use of convolutions to just represent the function once and apply it now to the different input components. And this gives us a very sparse representation of polynomials. And so we make use of these one-dimensional convolutional layers. And the fact that the Kolmogorov-Arnold representation consists only of univariate functions, or composition of these univariate functions. And now for these univariate functions, we can also get special existence results. And what is specific now, what is different now from the previous results that we have discussed, is that we don't actually have a target network, but we have a target function. So we can also need to think about the approximation error of the potential network representation of this function, but it also gives us more flexibility in order to consider different possible representations or neural network representations of this function, which will help us. So in this context, we can still, obtain similar results as before on the width. So essentially a width requirement. And what is interesting now in this context that it depends on, this is only, that it only depends on the square root now of the number of basis functions that we have, so the number of monomials that we have here. However, we also unfortunately have outside of the logarithm, we have the square root factor, square root 1 over square root over epsilon, which is the error that we're allowed to make. So this is not an ideal scaling, but this is at least for now for us unavoidable because it also takes the approximation, of the function approximation into account. So we would not have that if we would start from a target network directly. And otherwise, we get again just a logarithmic factor in even square root factors of the relevant parameters. And this gives us, and in addition to that, we also derive an improved general pruning construction for targets that now depends also on the depth. So if we use more layers to represent now a target layer, then also our width requirement becomes smaller, and there's a trade-off now between depth and width. And of course, we can also obtain special results now for univariate targets. But how did this contribute to solving our big questions that we started with? So you remember we had this problem that contemporary pruning algorithms don't find the lottery tickets that we are looking for, or have problems finding them. Let's put it like this, and for really complex and large-scale neural network structures. And our theory said, it should be possible. And what we actually also just derived is there should exist sparse targets. So the problem should not be that there don't exist targets. But now, of course, you could tell me, well, usually, we don't usually use polynomials, so these basis functions, right, necessarily to solve vision problems, for instance, or, most of the problems that we're interested in the natural language processing tasks. So maybe this is just, they are far more complicated or complex, and maybe in these scenarios that we care about, actually a sparse target ticket does not exist. So to rule that out, or at least to say, to test the second hypothesis, to test whether the pruning algorithms might have a problem or might be challenged and limited, let's design now an experimental setup in which we can actually check this hypothesis, that these pruning algorithms might have a problem and contribute to the problem. And this is work with my great collaborator, Jonas Fischer, who is currently a postdoc also in Harvard, where I was before. And we derived now a framework that allows us to exactly test the hypothesis that I was talking about. That is, we assume now we have a target network, a sparse representation of a problem, and a random source network. And the problem right now is that we don't know if this target network exists, right? So what we do is we plant and hide it in the source network, so to make it not that easy for the pruning algorithms to detect it. And then, use contemporary pruning algorithms, any pruning algorithms that we can come up with on the source network, for which we now guarantee that there exists a solution. And then we compare the result, for instance, with the target network, for instance, the sparsity of this target network. And we have done that now for 3 different problems: a standard classification problem, a regression problem, for which we can also guarantee that our construction is the sparsest possible solution, and an embedding problem, because these are kind of typical problems, that we face in machine learning. And then we tested. Now we did exactly what we did. We tested different pruning algorithms and looked how they perform. And it was actually really interesting to see that all pruning algorithms were not able to recover a lottery ticket that has the same sparsity, or a good as high sparsity as the targets that we planted. So this means that even though, of course, they are able to perform, to solve the tasks that we have defined on the synthetic data, so they're able to do that. However, they are not able to do that with a solution that is as sparse as we expect, which means now that we can really conclude these pruning algorithms have a problem. So, and there is potential for improvement. And with this, come also to the end of the talk, and let me quickly summarize what we have learned hopefully today. So I've presented you different lottery ticket existence proofs for general activation functions, for the case where the source depth is similar to the target depth. And we also derived that for, even though we didn't discuss it that much, but we also can derive that for really state-of-the-art architectures like CNNs and ResNets. And we could also even derive sparse neural network representation for universal lottery tickets. And to test whether, now this big open problem is, why this question that was that we were asking is why doesn't this pruning work as well as we expect for these really large scale complex models and problems? We devised now a planting framework that can also be used in practice. Could be used, to test now new pruning algorithms that really challenges state-of-the-art pruning algorithms and shows that we are not able to identify as sparse targets right now, or as sparse lottery tickets as we would expect. So with this, let me end that. Hopefully I have encouraged you to think about how we can improve the lottery ticket pruning algorithms, because they can really solve problems. They can help us democratize deep learning, and this is something that I think can only be a benefit for all of us. So thank you very much for your attention, and I'm looking forward to your questions.
Thank you, Rebekka, for this great talk. And I have a few questions, but before that, any audience have your questions, please feel free to either unmute yourself or post your questions in the chat.